Hello. Hello, everybody. I'm sorry I could not come here there because of the strict COVID measure, in particular in the re-entry policy. So I canceled to come to the Dresden. But unfortunately, but I will do the best. Please watching my video.
Good afternoon, everyone. First, I'd like to thank Professor Stefan Pascal, Chair of and Organizing Committee, for inviting me to MOF2022. I believe that this conference is enormously successful because of the extensive and meaningful content and lively discussion of MOFs and related porous materials. This is a commentary article published by Nature Materials, looking back on its first 20 years of publication. We were invited to contribute a report on the development and future of porous materials, especially MOF. As you know, MOF and other porous materials are now contributing to diverse fields in the environment, resources, energy, medicine, and health. When discussing the development of MOFs over the past 20 years, one of the leading indicators is to look at the current applications. On the other hand, as we know, such applications would not be realized without developing the basic science behind the materials, especially the chemistry of synthesis, structure, and properties. From this standpoint, this slide shows the chemistry and chemical engineering that led to the development of MOFs. We call these materials porous coordination polymers, PCPs, or metal organic frameworks, MOFs. Background of this chemistry is coordination bonds among these components. Today, I'm going to talk about the chemistry of PCPs, MOFs. Let's take a moment to review the history and terminology of this material. A coordination polymer is defined as a coordination compound extending through repeating coordination entities in 2 or 3 dimensions. The term was first used by Shibata in 1916. Interestingly, the coordination polymer using organic molecules from which MOF originated was synthesized using monovalent copper ion. The adiponitrile network in the upper left was synthesized more than 60 years ago. 30 years later, the diamond and honeycomb frameworks and interpenetrated frameworks were synthesized. These 3 networks have pores that are blocked by counterions. This framework we synthesized is the first example that contains an organic molecule. And in this paper, the author was the first to use the term metal organic framework, even though the 6 mutual interpenetrating framework makes it impossible to use pores. Coordination polymers are, of course, a subclass of coordination compounds. Among them, there are inorganic ICPs with cyanide ions or halide ions, and organic ligand bridging systems are OCP. Among the OCPs, those with potential pores are called PCPs or MOFs, according to the IUPAC task force team recommends. Let's take a look at the advancement of MOFs and discuss their characteristics. The first generation is the synthesis of networks. The second generation is the construction of robust porous structures. The second generation only became a reality when gas adsorption became possible. The third generation is flexible structure, which we call soft porous crystals. The fourth generation is exactly the next one. I'll start from the second generation MOF. Second generation MOF are truly robust porous structures. In realizing a second generation MOF with permanent pores, it is necessary that the MOF is stable with nothing in the pores, and that gas is reversibly taken up. We have synthesized a porous material in this scheme. In fact, it can reversibly adsorb methane, oxygen, and nitrogen. On the other hand, carbon dioxide has been adsorbed by materials synthesized in this scheme. With the advent of second generation MOF, this MOF chemistry has been actively studied worldwide. However, the big question was whether MOFs have essential functions not found in conventional porous materials such as zeolites. In 1998, I predicted the existence of third generation MOF and worked to discover it. In other words, it is a flexible MOF with a crystalline yet soft framework. It changes its structure according to chemical or physical stimuli and takes the optimal state. This is cooperative structural transformation phenomenon. The dynamic framework is one of the MOF's most outstanding and unique features. There are examples of early third generation MOFs. Deformations such as mutual dislocation of motifs and the framework expansion are observed. Since then, many researchers have discovered and developed diverse third generation MOFs. This is a timeline of their development. I'm sorry I can't show it to you in detail because I don't have a time. This is detailed in this review article. It has been common knowledge that crystals maintain their regular structure and undergo little deformation except breaking. Therefore, the creation of these crystals with flexible frameworks is a breakthrough in the history of crystalline porous materials. And the new sigmoidal curve adsorption isotherm, which had never been classified before. FX Coudert and I organized a Faraday discussion 2020 entitled Cooperative Phenomena in Framework Materials. The subject was the cooperativity of structures and functions of flexible MOFs and related materials. The contents and the discussion have already been published and can be found here. The discussion here are becoming more and more important, and I believe they have been carried over into the content of this meeting. We published a review article of the result of this flexible framework with an energetic interpretation to deepen our understanding of adsorption behavior. A point is that the loss of energy due to deformation is compensated for by the gain in interaction due to adsorption. Let's discuss the difference in adsorption and desorption phenomena between MOF with robust pores and soft pores. In the second generation robust pores, the isotherms are routine case classified as type 1 isotherm, On the other hand, an isotherm of soft porous MOFs has never been seen before. It's a sigmoidal curve like this. Note that the amount of adsorption, the amount of saturated adsorption remains the same. But if we look at the amount of desorption, on the other hand, there is a big difference in the recovery process. The adsorption gas can be taken out at a certain pressure without bringing it to a vacuum state. In other words, there is a big difference in the working capacity. This is one of the advantages of the flexible system. In my presentation, I will give examples here of recent major developments in third generation MOFs, focusing in the first storage, the second separation. First, concerning storage, the research stage has progressed from the discovery of flexible MOF to the control of its adsorption function. And I will show an example of successful control of its function in acetylene storage. As you know, highly reactive acetylene is an excellent raw material for chemical products. But the problem is that it is a dangerous gas with explosive properties. They react and explode at room temperature when pressurized to 2 atmospheres. This is an example of an acetylene cylinder that exploded. We've taken on the challenge of the safe storage of hazardous gases since early 2000s. This is the adsorption isotherm for acetylene, showing the 2 steps. Structural analysis reveals that this MOF compound, CPL1, initially expands and then contracts. The framework of MOF is flexible for gas adsorption. This shows a cross-section of a single channel in which acetylene is incorporated. The acetylene molecules are aligned regularly in a single row. The important point here is the double hydrogen bond between the acetylene and the oxygen on the surface of the pores. The density of acetylene in these pores is 200 times the explosive limit density, but it is still stably contained. Normally, pure acetylene is dissolved in acetone and pressed in a heavy cylinder, since it reacts explosively. If a cylinder filled with a MOF is used, a pure acetylene can be stably stored. Since we published acetylene storage in 2005, there have been many reports, as you can see here. The saturated adsorption capacity has been going up and up. However, when considering storage, it is not the amount adsorbed, but the amount that can be released. The working capacity is important. For this purpose, it is essential to develop a flexible MOF with a S-shaped adsorption isotherm, which maximizes the usable amount in a safe pressure range. The following conditions must be met for the practical application of gas storage. First, there is a need for porous materials that can be stored and released at room temperature and under pressure conditions that are not high. Second, explosive gases require additional storage mechanisms because stability is essential. Then it must be capable of storing and releasing an adequate amount of gas in the practical temperature and the pressure range. This third is a big hurdle. Generally speaking, one of our goals is to control porous properties by external stimuli. such as mechanical pressure change, light irradiation, application of electric fields. But in this talk, we're focusing on the pressure condition. We chose a flexible MOF with a doubly interpenetrated framework for this purpose because of our experience in developing the functionality of many of these interpenetrating MOFs, as shown here. This is a strategy for controlling and optimizing gate opening and closing pressure region for practical use. So the system stability is strongly connected to the total energy of ghost. The loss of energy due to deformation is compensated for the gain in the interaction due to absorption. To meet this objective, we synthesize an interpenetrating framework using zinc, bipyridine, 2,2' bipyridine, and benzene dicarboxylate. Here, BDC has a substituent such as amino or nitro groups. Here we adopted the solid solution method of mixing different ligands. This is a so-called multivariate MOF. The deformation energy is large for benzene dicarboxylate with nitro substituents, while those for BDC with amino group substituents. This is small. Therefore, the gate opens on the high pressure region for the MOF with more nitro content system. Therefore, it is clearly observed that the gate open and close pressure of the adsorption isosomes depend on the amount of the substituent. Once again, in the case of nitro content increases, this pressure goes to the upward. On the other hand, in amino case, is the downward. This is the objective and the result of this study. By changing the mixing ratio of substituents, we succeeded in moving the temperature and the pressure region, where acetylene explodes to obtain an effective adsorption isosome. We have obtained a fairly high usable storage capacity so far here. Next challenge is to address the issue of separation by flexible MOF. We propose a new mechanism to control the diffusion rate of guest molecules using special dynamics, also in flexible MOFs. We call this molecular diffusion by local dynamic motion, DLDM. These are two examples of interest in separations involving diffusion of existing materials. The first is activated carbon, a mechanism that utilizes pores of various sizes. The second is zeolite, where the presence and movement of anions in the pores affects diffusion. Both are very interesting, but not effective for separating very similar chemical species. I have discussed the function of structural flexibility. In addition to the structural phase transition shown in the crystal as a whole, the function of local motion at the molecular level is also useful. This movie shows how the local dynamics work while maintaining the overall structure of the framework. So it is separation using third generation MOF with local dynamics. We calculated the optical configuration of the ligand. The ligand adopted a twisted structure with a butterfly shape of the OPZ ring. We calculated the rotation energy of the OPZ ring and the result revealed that only relatively low energy is needed for rotation. We also calculate the flipping energy of the OPZ ring. The results show that the ligand has extremely low flipping energy. As a control, the vibration energy for cyclohexane is 46 kilojoule per mole, indicating that the ligand is somewhat flexible and quickly changes its configuration. This is a flexible MOF that incorporates a molecule with local motion. The molecule mimics the motion of butterfly's wing. When this motion is incorporated into the channel, it is controlled in a temperature-dependent manner. In this framework, the guest molecule diffusions smoothly, but at low temperature, it is difficult to diffuse due to the freezing of the gate. This is the adsorption isobar representing guest adsorption. The left is the normal case where the adsorbed amount increases as the temperature decreases. On the right, in the MOF with a gate in the channel due to the local dynamics, at certain low temperature, the gate motion freezes and closes. And the adsorption does not increase anymore and begins to decrease. The criteria to separate gas mixture are boiling point, molecular size, and shape. CO2 and methane are relatively easily combination to separate because their physicochemical properties differ. Whereas the separating mixture of acetylene CO2 and argon O2 are very difficult. Therefore, we make a challenge such a complex combination. For instance, we can see a big difference of isobar absorption between argon and O2. It can be recognized that these peaks clearly appear in different temperature ranges. Similarly, the ethylene and ethane, we can recognize that these peaks clearly appear in different temperature regions. This is what the movie looks like. In fact, mixture gases such as ethylene and ethane mixtures and oxygen and argon could be separated by the local motion of the MOF because of the different diffusion of the target molecules. Based on this idea, we developed the MOF 2 years ago that allows local motion to recognize the diffusion of guests and distinguish between those with very similar properties. Recently, a separation of mixture of propylene and propane has been reported using MOF with a channel that is different from our structure, but also make good use of local motion. Although there are only few examples, this third generation MOF is extremely useful for separation purposes. The last example is further development of this local dynamics mechanism, DLDM, to challenge the separation of water isotopologues. Chemists attempt to distinguish among isotopologues using simple strategies based on molecular chemistry, such as bond dissociation of water isotopologues via electrolysis or the use of host materials, such as cage compound or rigid porous materials, to capture one of the isotopologues. However, recognizing isotopologues has been difficult because of the inherently similar intermolecular structures and intermolecular interactions among isotopologues. Water isotopologues are among the most difficult isotopologue pairs to discriminate. In fact, the processes in industrial practice have very poor separation factors and are energy inefficient. The discrimination among water isotopologues using porous material-based adsorbents has not been proposed so far, even though they have been developed for decades. This is because of their very similar physicochemical properties, such as freezing point, boiling point, and bond energy. The chemical exchange equilibrium among H2O, D2O, HDO results in these three species always coexist once H2O and D2O are mixed. These lead to the significant obstacles to distinguishing H2O and D2O by traditional distillation and electrolysis methods. So here is our results. And so therefore, we attempt to separate these water isotopologues by defining the DLDS mechanism using the dynamic gate described previously. So here is the ligand system using we call DBAP-IPA, IDB-IPA, all isostatic acid derivatives having this kind of fluttering motion. So we synthesize the framework using the copper 2+. And the first one is we call FDC1, the second FDC2. FDC means flip-flop dynamic crystal. The other synthesized FDC1 possesses a cage structure. Cages are connected to the local gate of DBAP. Subsequently, FDC1 was subjected to vacuum at 393 Kelvin, resulting in its activated phase, FDC1A. FDC2A is similar to the FDC1A. This is a schematic structure of FDC with dynamic gates. When the temperature is low, the gate is narrow, but when the temperature is high, the system becomes like an open gate, and the capture water molecules move accordingly. These are the absorption kinetics curves for water isotopologues in the FDC system. On the left are the pressure-dependent desorption curves. On the right are the time-dependent desorption curves. The results show that H2O diffuses faster than D2O, and the absorption rate clearly indicates that the molecule is recognized. We carried out control experiments for the other small pore adsorbents, zeolites, Diff7, FMOF, other metal compounds, and like this. All these show the negligible difference in the adsorption kinetics of water isotopologues. So this is the dynamic description of water mixture of water isotopologues and using the mixed vapors. For instance, this is water isotopologues in the feed vapor. And this is water isotopologues in adsorption vapor. If the points are located on this 45-degree gradient line, no selectivity obtained. But our system, for instance, in very low concentration of water, concentration here, so after that separation, the contents increases for the very small one to the large one. The other compound showed like this. So this is very, very useful using this kind of local dynamics for the separation and controlling the gas molecule kinetics. Thanks to the third generation MOFs, this MOF science is growing ever more advanced. Furthermore, the fourth generation MOFs will be widely reached and contribute to our society, environment, energy, health, and medicine. Finally, let's talk about fourth generation MOF. I expect that the fourth generation will be the one with the attributes I abbreviate as HAD. They are those which control hybrid and hierarchy, anisotropy and asymmetry, defect and disorder, are intrinsic to structure and function. In particular, hierarchical integration of MOFs with different functions, hybridization with other functional materials, and crystal downsizing and thin film preparing for those purposes will be critical technologies. I'd like to mention the MOF crystal integration. 12 years ago, we synthesized a core shell crystal by epitaxial growth of two crystals. One with small pores, and the other with large pores. As you can see here, the outer one was size selective, and the inner one was capable of massive storage. Nowadays, a wide variety of MOF crystal composites have been synthesized, as shown here. There is no time to talk about each application, but the numerous possible applications show the development of MOF chemistry is progressing rapidly. Next topic is MOF and other materials hybridization. The chemistry of MOF hybrids has advanced greatly. This is due to, number one, the emergence of electrically and ionically conductive MOFs. Number two, progress in downsizing MOFs, especially in thin film technology. Since its emergence, MOF has been considered to be an insulator compound. However, in the past decade, many MOFs have been synthesized, ranging from semiconductors to those with metallic conductivity. The following is a list of 2D MOFs with electrical conductivity that will be highly applicable in the future. MOFs may now be considered electrically conducting materials instead of insulators. For this reason, it has many applications such as catalysts, sensors, and energy devices. The most interesting and applicable materials using MOFs are hybrid systems with other materials. In the past decade, there has been a great deal of progress and many new hybrid materials have been published. Due to time constraints, I can't talk about them all, but I think you can see the variety of chemistry in this slide. These include hybrid with organic, polymer, composite with metals, and of course, MOFs and the functional molecules and metal oxide and coals and so on and so forth. Here, as a result of two case studies on the application of MOF hybrids to sensors. New 2D conjugated electric conductive MOF containing copper units with mixed trigonal ligands was developed. This is Cu3HTB and THQ system. The gas sensors based on the disk materials nanowire thick film were fabricated on insulating substrate with pre-deposited gold interdigital electrodes by the drop coating method, followed by activation under flowing dry air at room temperature. So where layer structure grows here, like here. The dynamic sensing curves of this material over a broad range ammonium concentrations. 1 ppm to saturated vapor showed good response recovery properties at room temperature. Notably, the sensor showed good discrimination of ammonium in the low concentration range, 1 to 100 ppm. So, non-contact real-time detecting at the PPQ 1000 trillion fractional rate level. That is very important. Detecting low concentration gases is so to date, this kind of detection level are plotted like this. But still the missing in the exposed detection, the range around the PPQ to the PPT. Also, the explosive, hazardous, and toxic substances in non-contact ultra-sensitive sensors are required. And simultaneously, the biogas sensors detection is also required. We have designed a fabricated hybrid system to create a semiconductor with a large surface area. MOFs with specific entrapping enrichment effects on the target molecules, and synergistic functions at the interface between these two materials. The diagram shows the preparation of the titanium oxide MOF core shell structure. Firstly, we pyrolyze a layer of titanium oxide C crystal around 10 nanometer on the aluminum oxide substrate on the prefabricated electrode. Then hydrothermally grow the titanium oxide nanoarray, and after calcination and cleaning, directly put it into a master solution of MOF2022 for MOF cladding growth, and realize the regulation of MOF shell layer component thickness through parameter control. This is before coating, after coating. These are TEM image of CSV architecture of titanium oxide, the ammonium derivative MOF125. Here, this mill sheath constructed from integron ultra-thin nanosheet was quasi-oriented and uniform coated on TiO2. We have designed and fabricated a hybrid system to create a semiconductor with a large surface area, as mentioned, most with specific entrapping and enrichment effects on the target molecules and synergistic functions at the interface between the two materials. That is very important. So by using this unique core CSP architecture, we can detect the explosives. First, the capture explosives at the MOF cage, and by illumination, by light, the excited, and also this excited, the electron, the transfer, directed transfer to the titanium oxide, and also the oxygen reduction. So the sensing occurs. So all the processes can be realized in this system. So this material achieves the highest response to saturated RDX. This is explosives. Vapor, 4.9 ppt, and lowest detectable concentration, 0.8 ppq among the reported chemoresistive materials. So Today, I discussed further challenges and the possibilities for third-generation MOFs with examples. Based on the second and third generation, MOFs also discuss some of the science of the fourth-generation MOFs, which are expected to progress in the future. As you know, these topics were discussed in this MOF2022, putting them into larger categories like this: MOF fundamentals, function and properties, morphology, characterization, computer science, and commercialization. There are many target topics, and also 14 years ago, MOF conferences were started and have been held in countries around the world. During the time, dramatic progress has been made, not only in basic science, but also in the establishment of many startups for industrialization, which are working diligently to contribute to society. More and more startups are expected to be established in the future. We hope that more and more new companies will be found in the future. I believe that developing the chemistry of MOF will contribute to the society by addressing experimental challenges, energy usage, and resource utilization. Inspired by MOF chemistry, the chemistry of other families of molecule-based porous materials, such as COF and HOF, will also be developed, enabling other improved applications for societally important problems. Finally, I thank our collaborators and funding agencies for supporting us in advancing this study. Thank you for your kind attention.